Hello everyone. So we talk about in rotational motion. We discuss a couple of different equations. The last thing we discussed was force and how we define force in rotations, and we call it torque. So the next thing I would like to discuss is how mass is defined in rotations. Alright, so now for an example, let's say you have some mass m and then you apply a force. This is translational motion. As a result, the object moves some distance and it might accelerate on the way because of the force, and then we can write Newton's second law, F equals ma. Now when it comes to rotations, now this is called translational. The whole object is moving, right? Every point in the object is moving at the same time, in the same direction, same velocity, all that. When it comes to rotations, for an example, if we have a disk that is free to rotate around some point, instead of force we are applying a torque, right? So it could be for an example, a clockwise torque. So you apply a torque, as a result the object rotates. Now let's say you start from 0 and then you apply this constant torque. It is like applying a torque means you are applying a force from some distance. This force and the distance product gives you the torque, right? So let me remove these details. So you apply a torque. As a result of this torque, the object, this rotating disk, can start from 0 and it can accelerate. The acceleration is given by angular acceleration. If you apply the same torque on a, let's say, a little lighter object, same torque will have a bigger acceleration, right? It's smaller object, it's less mass, so the same rotating force can do more. If it is a heavier, bigger disk, much bigger than this, then the acceleration will be smaller. So in rotations also we can define something similar to this. In translational motion we have force equals mass times acceleration. In rotational motion, in rotations, similar to above, we can define something like Newton's second law. Torque equals something times rotational acceleration. What is that something? What connects torque into acceleration? What goes here? So you see that these two equations, if you compare F equals ma and tau equals this sum blank times alpha, they're kind of similar equations, right? They both have the same format. So here mass is replaced with something, and what is that something? So that's what we're gonna discuss. We call it rotational inertia. Rotational inertia, it's denoted by letter I and alpha. So this term I, so let's go here. Force is, the force equivalent in rotations is torque. Mass equivalent in rotation is rotational inertia, or I. Sometimes we call it moment of inertia. Same thing. Alright, so we can write this rotation, Newton's second law. We don't call it Newton's second law, but something looks like that. Torque equals I alpha. So when you apply a torque, a net torque gives you an acceleration, and that is equals to, torque is equals to the rotational inertia of the object multiplied by acceleration. Now what is this rotational inertia? Is it the mass, or is it something else? Is it more than that? So inertia of an object, rotational inertia of an object, we define it for rotating object, right? So that means you have to have, it doesn't need to be a circle all the time. It can be anything that rotates. It can be a rectangular object that is rotating around the fixed axis. It can be a cylinder that rotates around some axis. It can be a sphere. So for any kind of object, we can define rotational inertia. It does depend on the mass of the object, so it depends on the mass, and also it depends on the spread of the mass. So the spread, what I meant by saying spread of the mass is, think about this situation. Think about a thin cylinder. So let's say, let me erase this and make some more space. Okay, hold on. Alright, rotational inertia or moment of inertia denoted by letter I. I depends on mass and mass distribution. Alright, so in class I would have shown you some some demonstrations about these things, but here let's think about it this way. Let's say you have this rod, a uniform rod. You are rotating it around this axis. So it has some mass like 10 kilograms or something, and the mass is evenly distributed on this side, on the right side, and also on the left side. So when you try to rotate it, you feel some force that you need to apply. Now try to rotate it around one end. Take the same thing, but you rotate it around this point over here. It's the same mass, doesn't change, right? It's the same mass. Oops. But the spread of the mass over here, it's an even spread. The first one, it's on both sides, equal amounts. Over here, it's only on one side, so the spread or the distribution is not even. Therefore, you will feel that you need more torque in order to rotate this. So that's the idea of mass distribution. In other words, you can say inertia depends on the axis of your choice. Here the axis is to the center of this thing. Here it's in one corner. So based on where you place the axis, the mass distribution changes. So rotational inertia depends on the mass, and also it depends on the mass distribution. Another example would be, let's say you have a cylindrical object like this, and then you rotate it around this axis, right? And then the same mass, let's say you take it and you flatten this into a flat disc. It's still a cylinder, but it's more wider and less thickness, and then you rotate it around the center. If we compare the two inertias, the rotational inertias between these two objects, they both have the same mass, same number of kilograms. But if you think about the distribution, this is a more tight distribution, right? All the mass is more closer to the rotating axis. Over here, it's a larger distribution. The spread is bigger. So in this case, rotational inertia, or in other words, how difficult to rotate it. This one has a bigger inertia, this one has a smaller inertia. Same thing here. Small inertia, big inertia. More spread, more distribution you have, a bigger the inertia is. It's like the reluctance to rotate, right? So that's the idea of rotational inertia. Okay, so that's the idea of this, and then we can say tau equals I alpha. We'll get to this later. We'll work on some examples, but before that, let's talk a little bit more about the inertia. Alright, so let's look into rotational inertia a little bit in detail. So I mentioned that it depends on the mass and mass distribution. So different shapes, different objects will have different rotational inertias, and for certain common shapes, certain common objects like cylinders, spheres, or what else, discs, or hollow spheres, hoops. So we have set equations, and I will give those equations to you guys in a minute. But what's the most simplest case, or the fundamental case? The most simplest case is a point particle, a point mass. So let's say here we have a point-like mass with mass m, and it's rotating around a fixed point. So this is the fixed point, and it's rotating around this fixed point with a radius r. So it's going like this. Now what is the rotational inertia, or moment of inertia for this point mass? It's defined as I equals mr squared, right? Mass multiplied by radius squared. So this tells you the unit of this is kilograms meter squared, right? That's the unit. So for an example, if we have a point-like object with mass equals, let's say, 2 kilograms, and it's rotating in a circle with radius of let's say 3 meters. So the inertia, or moment of inertia, I keep saying inertia, it has to be moment of inertia or rotational inertia, is mass times radius squared, 2 times 3 squared, so 2 times 9, which is 18 kilograms meters squared. Alright, so this is how you find rotational inertia of a simple point-like mass. Okay, so that's the simplest case. Now let's look at some more commonly found shapes or objects. Alright, so let me erase this. Okay, so rotational inertia. Let's make a table. Now we know that the simplest case, a point mass, around some given point r, is mr squared. One second. So these, you don't have to memorize these. In the exam, I will give you these numbers, I will give you these equations, but for your reference, I'm going to give you a list of equations. Okay, so hold on one second. A solid cylinder, so here's a cylinder, a solid cylinder with a radius r. Okay, so radius r, and mass m. So radius r and mass m, rotating around this center axis. So the solid cylinder, that means the whole thing has matter in it. All right, so the equation is given by half times mass times radius square. How about a sphere? Again, a solid one. Solid sphere with a mass m and radius r is given by 2/5 mr squared. Let's look into a hoop, a thin hoop. With mass m and radius r. So it is something like this, right? A thin hoop, okay, around this axis. It's given by mr squared. It's kind of similar to a point particles equation. All right, let's look at few more shapes. How about a cylinder but a hollow one? Now when we say solid cylinder, this can be a disc as well, right? It doesn't need to be like a thin long object. It can be something like a flat disc. This also can be considered as a cylinder, so it has the same equation, right? So it goes here also. All right, how about a hollow cylinder? So it is something like this. There's a cylinder, but inside is empty, right? You get the point. So this is where all the mass is. It's like a tube. So for something like this, there has to be two radii, right? The inner radius and the outer radius. So we'll call this the inner radius r1 and the outer radius r2. And the mass of this thing, mass is all concentrated in this shell kind of thing, right? Inside is hollow. So that's given by half times mass times r1 squared plus r2 squared. So little r1 squared plus r2 squared. What else? What else do we have? Okay, so a uniform rod or like a rectangular object. So something like this. Let's say a uniform long rod, something like this. Let's say you are rotating around this axis, has a mass m and length l. For these things, the mass and radius, right? For this one we said length is l. So when I say l, I'm talking about the total length from here to here. And moment of inertia is given by 1/12 ml squared. Now the same thing we can rotate it around a different axis, as I showed you before. Let's say it's the same thing, length l, but you are rotating around this axis, m and l. Moment of inertia is given by 1 over 3 ml squared. You see, this is 4 times bigger than rotating it around the center axis, right? Okay, so I think this is enough. We have a couple of different shapes that we commonly use. No need to memorize any of these equations. In the exam I can give you those, or you have your notes, and the exam is usually, take home type. So you have your notes, you can use them and figure out what the equation is. Okay. Alright, so it will be a good idea to write these things down somewhere in your book, so whenever you work on problems, you have it in your hand. Alright, so these are the equations for rotational inertias. Once again, what is rotational inertia? It's the mass equivalent in rotations. So if you are using an equation like something similar to F equals ma kind of equation, you replace, so let's say this is in translational motion, but if you are trying to do the same thing, like what happens to an object's rotation, how fast it's going to rotate, and you apply a torque, we replace these terms. We replace this by torque, replace this by alpha, this is replaced by moment of inertia. So now you have this equation. And remember, to go from mass to inertia, you need to know the mass. Also, this particular equation, like for an example, if it is a solid sphere, you need to know the mass plus the radius, and then this 2 over 5 constant in the front. Okay, so that's how you convert a mass into an inertia. Okay, so let's try one or two simple examples. Okay, so I am going to erase this. You guys should write this down somewhere because we're going to use it again. Okay. Alright, let's try an example. Here's the example. Find the moment of inertia of a 10 kilogram sphere of radius 0.6 meters when the axis of rotation is through its center. We have a solid sphere, mass equals 10 kilograms, and the radius equals 0.6 meters, and you are rotating through an axis that goes through the center. So this is important to mention where the axis is, but of course you can rotate it around an axis that goes little off to the center, right? It won't be symmetric, but still you can do it. So for this we have to use a different equation for moment of inertia, because the equation just I gave you is defined for all these common axis that goes through the center. So how do you find I? I is given as, for this particular one, if it is a uniform sphere, that will be 2 over 5 mr squared. So 2 over 5, 10 times 0.6 squared. So need the calculator. 3.6, 3.6, 7.2, 7.2 divided by 5, 1 point something I guess. 6 squared multiplied by, we get 1.44 kilograms meter squared. Right, so that's the moment of inertia for this object. So you can take any shape, any particular object, and then if you know the details of it, so for an example, if we have a rectangular object like this, let's say mass is 3 kilograms, length is what, 2 meters, and you want to rotate it around the center. So I is given by 1/12 ml squared. Right, so you just plug the numbers. 1/12, 3 times 2 squared is 4. So okay, this is nice, just 1 kilogram meter squared. If you rotate the same thing around an axis along the edge, it's going to be a different number. So that will be 1/3 ml squared. 1/3 times 3 times L squared is 4. So this will be 4 kilogram meter squared. Okay, so this is how you find the moment of inertia, rotational inertia, the mass equivalent of an object. Okay, so that's done. Let's see what we have next. Okay, so how do we know that this is the equation for this particular shape, or this is the equation for this particular shape? Now, through experimentation and a lot of mathematics, these equations were developed. You guys in college physics, you don't have to worry about it. I will give you the equations, but if you are in university physics, you need to have a little bit of an idea where these things coming from, how to derive these equations, how to develop them. So we will talk about that at the end of the lecture, at the end of this. So that will the last few minutes. I'm gonna go back to these equations and show you how to get these. College physics, you don't need to worry about that. Okay. All right. Let's see what's next. Okay. So now we know that when it comes to rotation, mass is replaced by moment of inertia, or I. So with that, we can define all these most of the known equations. Like for an example, F equals ma. In translational motion, the rotational equivalent is tau equals I alpha, right? Mass replaced by inertia, acceleration by angular acceleration. Momentum, actually momentum in rotations is a whole chapter, it's a whole new chapter, but let me briefly mention that. That's why I went back to see whether it's included here. So momentum, we know that it's P equals mv, right? When it comes to rotations, we replace linear momentum with something called the angular momentum, represented by L. That is I times mass replaced by moment of inertia, velocity by omega. Now this is something, this L is something we haven't discussed before, so some other time we'll go into that. For the time being, I'm just going to show you the equation. In kinematics, another important thing is kinetic energy, right? Kinetic energy, half mv squared. Now, I think you guys know how to replace that. Rotational kinetic energy in rotations is half times I omega squared. So we will work on few examples related to these equations, especially this one and this one over here. Momentum, maybe we'll discuss it later. So having said that, that is the end of this discussion. We will work on examples in class when we meet next time. So that's it. Now with university physics, I'm going to spend a few more minutes about how to derive these equations, but everybody more than welcome to take a look at it. All right. Okay, so let's erase this. Okay, how to find the moment of inertia of an object. Now, moment of inertia. The simplest case is a point particle with mass m with some distance r from a fixed point. So if it is rotating, what's the moment of inertia? Rotational inertia. It doesn't need to be rotating. We can, even if it is stationary, we can still define what the inertia could be. Okay, and it is given by I equals mr squared. Now think about a solid object, like something like this, has some big mass, and you want to find its rotational inertia around some point like this, some axis like this. So what do? We're gonna divide this into lot of small masses like this, right? Millions of those. So each mass we can say, so for an example, this guy, this is mass I, and it is at a distance, if you measure the distance, at a distance r I, ith distance. So for that little piece, that little inertia, the ith inertia, or let's say, yeah, inertia of the ith piece is mi ri squared, right? So the inertia of the whole thing, the total mass, total object, is what? The summation of all these little inertias, which is summation mi ri squared, right? You're going to add all these little pieces. Take this piece, multiply with this distance, take this piece, multiply with its distance. Likewise, you're going to add all the little pieces with their distances. You can't take the whole thing, the entire mass, multiplied by some random common distance. That doesn't work, right? Each piece has to be multiplied by its own distance. So if we divide this into so many tiny little pieces that like this, we make this little mi as small as possible, right? Make it smaller and smaller. At some point we can say this little mass is going to become dm, right? A small mass. So then we can say the total I equals the integration of all these dm's and their respective r squared. So we have to add all of them starting from 0 and add all of them, do an integration. We get the total moment of inertia. Okay, equation looks very simple, but using it in practice is going to be a little tricky. So let's look at the simple case. Let's say we have this rod, a uniform rod, and fixed around one end. It's free to rotate around this point, has a mass m and length l. Okay, so we want to find what's the moment of inertia is. We already know what the equation, we try to derive it, so that's the goal. Okay, so I have a feeling that this is not enough space, so let me clear this whole thing and get a new page. Okay, so this is what we have. Here's solid object. We're going to rotate it around this point, and mass is m, length is l. Okay, so the way we're going to do this is, we know that for a point like mass, the point mass at a distance r, inertia is given by mr squared. So if you add all of these, we get the whole thing. So that's the same thing we're going to do. We're going to take a little random piece like this, small piece, let's call it dm, the little mass, at a distance, let's say x. So for this little dm piece, inertia equals, we know that it comes from mr squared, so that will be dm x squared, right? What we need to do to get the total inertia is integrate all these dm's and x squared, all the little pieces from one end to the other. So how do we do that? This is a mass term, this is a distance. We can't integrate two different things. If you are integrating x, you have to have dx. If you are integrating, like you know what I'm trying to say here, right? The variable and the integral, they all should have the same format. So we're going to keep this x, but we're going to change this dm, and we're going to write the mass. So that's the trick. We're going to write this mass in terms of some x letters, some distance quantities, so that we can integrate this. So how do we do that? How do we write a mass using a distance, right? We have never done this before, I think. So we're going to try a trick here. If I redraw this diagram over there, make it a little bigger. So this piece dm, I say that this length, this distance is dx, right? It has some thickness, which is dx, and it is at a distance x from the center. Now how do I connect this dx to dm? I'm going to define something called the linear mass density. Don't think too much about this term, linear mass density. What I do is I define some new variable, a new term, lambda, which is the total mass divided by total length, mass divided by length. So in other words, this is mass divided by length, means this is like kilograms per meter, like the mass per unit length, mass per meter. So if I now if I have the length, and if I know what lambda is, then I can find the mass of that thing, right? This is mass per unit length, so mass becomes lambda L. If I know lambda and if I know L, I can find the mass. So in the same way, dm is lambda times dx, right? And lambda I can find if I know the mass, 10 kilograms divided by 2 meters, I get lambda, for an example. So using this, now I'm going to replace this integral using that. So I have I equals integration, instead of dm, I'm going to write lambda dx x squared, and I'm rotating around this point, right, over here. So my x starts from 0, go all the way to L. This end is L. So 0 to L. So what do we have? I equals, now lambda is a constant. Yes, lambda is the total mass divided by total length. Total mass is a constant, total length is a constant, so lambda is a constant, comes out 0 to L x squared dx. And you know this, you know what to do with this x squared dx. Okay, write it here. Lambda lambda x squared dx is x cubed over 3, I believe. I think so. 0 to L. If this doesn't work, I'll come back and change it, right? I think this is right. Alright, so going from 0 to L. Now lambda times I have L3 over 3. 0 is not going to do anything, right? Okay, now what is lambda? Lambda I know m over L, so m over L, L3 over 3. So now you see one of these L's cancels out with this guy and gives you a square. So here we have I equals ml2 over 3. Or we can rewrite this 1 over 3 ml squared. Okay, so if you like the challenge, give it a try and prove that moment of inertia around the center is I think it was 1 over 12 ml squared. So this time, I don't know, you can go from, like, you can write this is negative L over 2 and L over 2, and then go from change the limit like that. So that will be an interesting thing. Imagine doing this for all the other shapes. Those are real fun math problems. But I'm not gonna go there. You don't have to do that much. I want you guys to have an idea about these simple cases. Okay. Alright, so that's it. Thanks, guys.